Hello guys, hope you're doing well. My name is Mahmoud Kiasari, and today we are going to talk about another chapter of advanced algebra. So without further ado, let's talk about it. So at this chapter, we are going to talk about the matrices. We somehow have some kind of idea that what are they. We talked about the row, about the column, about the degree, about the determinant, and any other kind of things. But right now we are going to talk about it in detail and say that actually matrices are going to be more advanced concept. It means that we can use them as functions. They are going to transform numbers or vectors from one space to another space. So this chapter, we are going to talk about it in detail. Stay tuned and let's see what's going on. As I just mentioned, matrices actually are more than numbers. They transform space. So the very first thing that we have to understand is, what does it mean by transform? What is the terminology? What is the definition? So at this point, a transformation is going to be a function that takes input vectors. We know about the vectors. The vectors are just numbers that they can have x and y if we are talking about the 2D dimension. They can have x, y, and z if we are talking about 3 dimension. The vectors are going to move one number from one place or to another one, or is some kind of displacement, as we all know from the previous videos, and produces output vectors. In essence, it moves points around. So the two rules that we have to be careful about the linearity is that right now we are going to talk about the vectors. It means that we are not going to touch any curve or any non-linearity or any other kind of specific types of curves that we were talking about, or parabola, hyperbola, or whatever is that. Right now we are only talking about vectors. The origin stays put. What does that mean? It means that the zero vector always maps to the zero vector. So it means that the 0, 1 is going to just map to 0, 1, and we are going to have our 0 and vertex. So this is nothing new. Grid lines remain parallel and evenly spaced. So if something happened after just doing this transformation, the grid lines that we had, which we call this guys at grid lines, they are going to stay still in parallel and evenly spaced. It means that they are not going to change. Maybe they are going to skew, as you can see from this transformation, we have this, but still they're going to remain parallel and the space is going to be even. It means that lines remain lines. They don't curve or break. Again, we are talking about the linear condition. This is a consequence of preserving vector addition and scalar multiplication. Imagine that we do have the condition of vectors could be like this. Then by using a matrix, which we were talking about, we are going to talk about it, how actually is going to do that. We are going to transform to this. Obviously, the vector is going to change, and also the grid lines that we have is going to change, but the zero vector, or the one that we have in the center, is going to stay the same, and also the space between your grid lines are going to stay the same, and both of them are going to stay still parallel. So here's the matrix. This is the engine, or this is the essence of transformation. Any linear transformation in 2D space. Right now we are only talking about the 2D. It means that our matrix is 2 by 2. If we were talking about the 3D, it should be 3 by 3. It is a little bit complicated, so we are not going to touch that right now. Any linear transformation into this 2D space can be described completely by a single 2 by 2 matrix. The matrix is going to act on a vector to produce a new transformed vector. As we just talking about it, the matrix is going to work on specific vector. Right now, the vector is just like the input of your function. If you guys remember, y equals f of x. F was acting as a function. It was a machine that is going to get x as input and is going to give you something as y. So the matrix acts on a vector, and in order to produce a new transform vector, this action is defined by matrix vector multiplication. It means that if I do have a case like this, I do have the couple of input vectors, and these guys are going to be injected inside my machine or my matrix. Then the output would be the multiplication of that matrix and vectors. And obviously it's going to change the space, it's going to change the values, maybe sometimes change the direction, and so on. So t at this point, t of v of x is going to be a times v. T is the transformation, v is the original vector. It means that it could be any of these guys, and a is the matrix that defines this transformation. A is your machine, like the function or f of x. So the very first example that we have is about uniform scaling. What does that mean? In this transformation, we are going to only stretch or shrink the space equally in all directions. We are not going to make it some kind of skew it. We are not going to flip that. Maybe at some points, if our matrix is going to have some numbers that's going to be negative, it's going to be flipped. But right now we're talking about positive. So nothing strange is happening to our circuit, to our vectors or to our space. The only thing that is happening is going to be multiplied by the number that we do have in the uniform scaling. A uniform scaling is a 2 by 2 matrix, and based on the numbers we do have, as you can see, it's just like a matrix that is diagonal going to be the same. And if both of them are the same, 2 and 2, like 1 and 1, like 3 and 3, at this point, your matrix is going to stretch or shrink the space. So the matrix at this point is going to double the length of every vector. We know that we do have the x-axis part that we show the smallest step by I step, and we do have the y-axis step. We do show it as with j. So the matrix is going to double the length of every vector. The direction is preserved, but the magnitude is changed by a factor of 2. It means that at this point, I do have a space and I know its area is going to be 1. By using this matrix as a transformation method, I'm going to double every side of this square. And if I do that, my area is going to be 4. Obviously, I do have doubled. So the only thing that is happening, I'm just stretching my space, nothing more. Then let's talk about the stretching and squishing. It means that at some points I do have a matrix and the number that we do have on the diagonal part are not going to be the same. It means that at this point my x-axis or y-axis or my x space and y space are not going to be transformed equally, and they're not in balance. At this point, one of them is going to stretch more, one of them is going to just shrink. So it means that at this transformation, scaling space differently along the x and y axis. What is the effect? The matrix doubles the x component. It means that whatever we had over here is going to get doubled like this, and halves the y component. It means that whatever we had over here is going to be half like this of every vector. It stretches the space horizontally, y compressing it vertically. So as you can see over here, is going to be useful for changing aspect ratio or modeling some kind of physical effects. Then we do have the flipping, because the only number we were talking about so far was positive. So what would happen if we're dealing with negative number? At this point, imagine that the only thing I would like to do is just flip based on what? Based on y-axis or maybe both of them. So I do have a matrix and I do have 1 and I do have -1. So this guy is going to mirror the space across an axis. And what is the axis? Since at this point I do have 1 is related to x, well, 1 is for the first column related to x-axis, and the second column is related to second axis or y-axis, I can somehow imagine that my kind of space or some kind of the vector that I have is going to be flipped based on the y-axis. So this matrix is going to flip the y component. As you can see over here, we had something like that one. It would be vector, and we do have a step like this and like that. And our vector is going to be flipped. And if this gets flipped, it means that like this. So right now, the x-axis is going to be my what? It is some kind of the x-axis is going to be my mirror, and this guy is going to flip. So please accept my apology. Over here, I meant by y-axis is that my y is going to be flipped. So it means that it's going to move, it's going to reflect through x-axis. So the x is going to stay the same, but y is going to be negative or going to be flipped. So it means that y is going to change. Our x is going to stay constant, and it means that whatever vector that we had is going to flip through the x-axis. So at this point, we do have the matrix flip the y component of every vector, effectively reflecting the entire plane across the x-axis. So geometrically inside, if you know that the determinant of A, B, C, D, the determinant of this guy is going to be AD subtracted by BC. So if we consider that the determinant of this guy, at this point we can say that the determinant of the reflection or the flipping space over the x-axis is going to be what? Is going to be -1. So this guy indicates a transformation that flips the orientation of space. As we just talking about it, I do have a vector like this, and I'm using this transformation. I'm going to move it like that, so it's going to be like this one. It's not that kind of complicated. So what about turning space? What about if I would like to rotate this space? At this point, we are going to rotate the entire plane around the origin by a certain angle. So it means that at this point I do have my whole space like this, and then I'm going to flip it, or not flipping it, I'm going to rotate it through an angle. That this angle is going to be what, from for example here, is going to be theta. So theta is going to convert my space to something like this. As you can see, the space is changing, the vectors is changing, and let's see how we can have a dedicated formula for that. So the matrix for rotation has a specific construction for that A as our matrix or function is cosine of theta, sine of theta, and negative sine of theta. So by finding the determinant, you can see that how we can find the determinant. It would be cosine theta to the power 2 subtracted by negative sine of theta times sine of theta. If you find this one, finally you would have cosine of theta to the power 2 plus sine of theta to the power 2. In some kind of mathematics, this formula is going to give you a number as 1. It doesn't matter what number you use, could 45, 60, whatever number you use, cosine plus sine of theta to the power 2 is going to be 1. What this guy is giving us, this guy says that the only thing that I'm doing is just changing or rotating your space. Since your determinant is a very important concept and terminology of each matrix. It's going to show you how that specific matrix is going to behave. By finding the number of determinant, we know that at this point, we are not going to have any scale. We don't have any shrinking, we don't have any stretching, so everything is the same. The only thing that would happen is that my space is going to rotate by 45 degrees or whatever the angle of theta is. So every vector is rotated by the angle of theta. Again, we are talking about the positive of theta talks about the counterclockwise. So whenever we do have the counterclockwise, means that our theta is positive. If we are moving clockwise, means that our theta is negative. So every vector is rotated by the angle of theta. Length and the angles between vectors are preserved. It means that they are not going to change. If they are 90 degrees or whatever do we have, they're going to stay at 90 degrees. So geometric insight, a determinant of 1, as I just talking about it, a characteristic of a transformation, like pure rotation. Again, no scaling, no stretching, nothing. That preserves the orientation of a space. Whatever you had is going to stay the same. At this point, imagine that I do have negative and 0.7. So 0.7 actually is, we can find the angle itself. If consider that cosine of theta is 0.7, if you find the theta itself, it means that you find the cosine inverse of 7 should be 45 degrees. So at this point, you know that your space is going to rotate by 45 degrees clockwise. I'm sorry, counterclockwise. So what about the orders? Because at some points you're not only having one transformation, maybe sometimes you have one after another one back to back. So order at this point matters. It means that the concept says applying one transformation after another one is equivalent to multiplying the matrices. It means that instead of finding one of them, then to move to another one, the thing that we can do is in order to simplify everything to find the multiplication of transformers. It means that at this point, imagine that I do have my concept, I do have my matrix, which is the first one is T1, and the T2 is for matrix B. So applying T1 then T2 correspond to the matrix B times A. It means that using the T1, or for instance the function that we have, and if I consider it as A matrix is responsible for the first transformation, B is responsible for the second transformation. If I would like to have that, I should have my first transformation, then I have to multiply the second one based on the matrix multiplication. It's not dot, by the way, it's multiplication of multiplication of matrices. We know about that. And if you have another one like C, it should be like this. If you have another one like D, it should be like this. Why I'm saying that? Because matrix multiplication is generally not commutative. What does that mean? If you guys remember about the algebra, we had something like this. It equals B multiplied by A. So that was right, because the only thing that we had was just about the numbers. We didn't talk about the vectors, we didn't talk about the direction. But at this point, it matters. So A times B, it's not going to be equals to B times A. What does that mean? It means that AB right now says that first of all, do
the B or B transformation, then do A transformation. But B times A says that first do A transformation and then do B transformation. Applying the rotation, for instance, where we are talking about the first one as applying the rotation, and then we are talking. So imagine at this point, there's some kind of A and B is going to say one of them is rotation and another one is shearing. So it's, as I just told you, the ordering matters, and it doesn't say that first you can rotate then shear and another step would be shear and you can rotate, because these two are not the same. Let's imagine that I do have this space, I do have this guy, and I would like to first rotate and then shear. If I do that, I do have a rotation by 45 degrees and I do have shear. It would be something like that. If I do the second path, I do have the shear at first and then I'm going to rotate that. Obviously, as you can see, these two guys are not look alike. That's why important to which one comes first. So ordering matters, and based on that, we are going to do the multiplication or the matrix multiplication. So here's the secret. What happens to the basis vectors? Because those are important part. Those guys are going to help us in order to see that what is actually happening. So here's the insight. To understand any 2 by 2 matrix, you only need to see where it sends the basis vectors. What was the basis vectors? We had I and J as basis vectors. So the first column of the matrix is the vector where I is equals 1 and 0. Is that so? It means that at this column, we are talking about what? We are talking about X. The second column of the matrix is the vector J lands. We are talking about this one. Whatever is happening in the first column and second column is going to give you an idea at what is happening inside the whole circuit. So this is going to be Ix new, Iy new, and this guy is going to be Jx new and Jy new based on their x-axis and y-axis. So here's another terminology, image. What is that? What space remains after transformation? Because this is a very important concept. There are some times that you do have a transformation that is going to make stretching, make some kind of flipping. That is okay. But at some point, you're going to lose something. You're going to lose some dimensions. So let's see what is happening actually. Let's see what is the definition of image. The image or range, we have two names for that, of a transformation is the set of all possible output vectors. We had something around span in the previous videos. It is something like that, but with a little bit of difference. So the image is the span, as I was talking about it, of the transformed basis vectors. It's the space painted by where I and J land, because if we understand that where I and J lands, we can understand all of this, everything related to transformation. If a transformation squishes the entire 2D plane onto a single line, imagine something happened and I do have 2 dimension, but because of my transformation right now, I don't know anything about it, I just converted it to one line. I just got rid of one of those axes, or a squeeze pose axis, to one axis. Right now, I don't know what that axis is, it's just hypothetical axis, but the important thing is right now I converted all of my x and y into one axis. So the image is that 1D line, and we are calling the dimension of that image as rank of the rank of that specific matrix. So as I told you, imagine that we do have this guy, and at another point I and J are going to be some kind of squished with each other, and finally I'm going to have only one line. So on that point, let's say that the rank of my image is going to be 1. So the rank is something related to my matrix definition of rank itself. So what space is lost to the origin? So the kernel or null space of a transformation is set of all vectors that are squished down to the 0 vector. So right now I'm going to find how many actually of vectors are just squished down, or to see a 0 vector are going to some kind of being destroyed. So the geometric intuition, it says that the kernel represent the directions that are lost or collapsed by the transformation. As I just told you, we are going to lose something. So we are going to talk about in detail what is happening, how many vectors, how many axes actually we lost. For a transformation that projects all of space onto the x-axis, any vector lying on the y-axis, for instance 0 and 5, it gets mapped to 0 and 0. So at this point we can see, because of this transformation, we are going to lose what? We are going to lose the vectors that only going to be online. We are going to lose the vectors So at this point, something is happening because of the transformation, and all of the y-axis, or all of the y numbers that I had related to vectors are going to be dead, or going to be destroyed. So at this point, we say that the entire y-axis is going to be as kernel, and the dimension of the kernel is going to be something we call as nullity. Imagine that I do have a vector like this. I do have a couple of vectors, and they're going to be like that. But after some transformation, I'm going to lose everything related to y, and all of them are going to be projectile over the x-axis. At this point, I say that the kernel is y and the nullity is going to be 1. So let's have a full picture. What remains vs what lost. So the dimensions of the image, the one that actually we are going to have it at the end, and the kernel, the one that we are going to lose, are fundamentally linked. Again, what was rank? Rank is the dimension of the image, is the output space. Whatever that you have over here is going to show you about how many dimensions you have is going to be something we call as rank. What is nullity? Nullity is the dimension of the kernel, the input space that gets lost. On the previous example, we had the y-axis that's getting lost, so we call it as nullity. And the Rank-Nullity Theorem, this is a very important one. For any linear transformation, the dimensions of the input space are perfectly accounted for by the dimensions of the output space. It means that your input space and output space are really connected to each other, and the collapse space. So on the other hand, I can say that the dimension of the domain that I do have is related to rank, is related to image, and nullity, some kind of the axis that I'm going to lose. At this point, I know the dimension is 2 for the input vector, right? But something happened, and for my output, I do have the rank of 1. Right now, the only axis that I have is the combination of x and y. It's going to be one axis by itself. I don't know what is that, but they only follow one thing. So the kernel at this point, or nullity, was the one that actually lost. So obviously the dimension, or the dimension of the whole thing, of the input vector or domain, is going to be combination of kernel and the image itself, and we do have 1 plus 1 is going to be 2, just in case if we didn't have it. So let's see a couple of special transformation. All linear transformation can be understood by observing where I and j land. These 2 steps, or basic steps, are important. So identity, what is that? The identity is the one that, like the guy that we do have it at the very beginning, that this guy actually is doing nothing. It's not going to change anything at all. This guy is just say that whatever you had at the beginning is going to be the same. So this guy is identity, and it's going to do nothing. What about the projection? Projection would say that I'm going to keep your x values, and I'm going to demolish your y values. So y is going to be kernel, and my image is going to be 1. So at this point, for instance, we do have projection onto x-axis is going to collapse the space into only one line and everything related to x. Obviously, if you would like to have the y, we can make it 0 and make this guy y. So the shear means that slant space while keeping one axis fixed. At this point, you see that this guy is going to consider as shear, so it's going to keep one of them fixed while somehow rotating another one. So at this point, my I is fixed, my xbox fixed, but j is going to change a little bit. So what determinant says, as I just told you, determinant is a very important number that can give us some clue at what is actually happening to the whole system. So this determinant of a matrix tells you how much the area of the region is going to change after transformation. Imagine I do have this area, whatever it is, or just imagine that I do have it squared. It could be anything, whatever the area is related to anything. Just imagine that I have like this. And after that, using this transformation, using this matrix, I'm going to have the area like this. Maybe one question would be that if you have this transformation from the first guy to the second guy, how much your area would change. Right now, by finding the determinant, we can find the magnitude. So the determinant of A, the factor by which area is the scale. If determinant, for example, was 2, the area is going to be doubled. If determinant was 0, it means that the space collapsed to a lower dimension, right? The determinant of 0 could be something like this. As you can see over here, the determinant was A times B. Let me just get rid of that. This is the A times B. This guy times B subtracted by this guy times B. So since the determinant is 0, means that we don't have any area. The area is completely meaningless at this point because one of them is collapsing. So the sign over here is somehow important because it indicates if the orientation is flipped or not. If you guys remember, so far we were talking about the positive sign, but at one point when we had something like this, at one point, if I do have 1, -1, 0, and 0, it was one of the matrices that we were talking about, the determinant of this matrix is going to be -1. So it means that this guy is going to be identity, that's okay, but it's going to flip it based on what? X is going to stay the same, Y is going to be negative or flipped. So it's going to change through the x-axis. And if the determinant is smaller than 0, space has been turned inside out, right? The reflection itself. So we had some kind of example. If you find that the determinant of this matrix is equal to 3, so this says that your area is going to scale by the factor of 3. From numbers to geometry, conceptual summary. So right now we are going to talk about whatever we learned. The very first thing that we learned was about that matrices actually are functions. They are not going to be just normal things that we use them for multiplication, addition. No. They are far more than that. They take the vectors as an input and they are going to give us a new output. They are going to be transformed vectors. Then we talked about the columns are the key actually. The columns of a matrix are the destination of the basis vectors. About bits to basis vectors were I and j. That by having knowledge about these ones, the I and j's, we can tell everything about this transformation. Then we talked about the image and kernel. The image is the space that remains, while the kernel is the space that is going to be lost. The image, we talked about something as we know about rank, and then we talked about the kernel means that everything that we are going to, or the space that we are going to lose. For example, y-axis, x-axis, or any kind of dimension. Finally, we had the determinant. The determinant is going to be a single number that reveals so many things about our transformation. So far we learned so many things related to matrices, and those guys are going to be so useful in our transformation from one space to another one. So try to rewatch the video. If you have any question, I will be more than happy to answer you. My name is Mahmoud Kiasari. If you enjoyed the video, please don't forget to like, share, and comment. That will be so helpful for me. Have yourself a great day, night, whatever. See you around.